I don't know how audio is going to be because if you guys are talking or if I'm talking or pointing at things, it's probably going to be all messed up. But having sat through it and then watching it, you should be able to follow along just fine. So um, we're just going to start new. So go really basic. We're just going to do a tube and make flow through it. So we can go through all the steps required. I need to change those two options so I can pick my power right away. Yeah, the only downside is it runs a little bit slower with the recorder, so you will either hate that as you're going through it again, or you're going to love it because everything's going to be nice and paced. So, exactly. If you guys can work with two screens, I would suggest taking any of the videos I use and just put one on one screen, make it full screen, and then just mirror kind of exactly what I do through each of them. That's what I did when I had videos or like when I look at stuff on YouTube. There's also a lot of stuff on YouTube if you want additional material. Let me know. I can make videos to cover it. I think that's like the fourth or fifth time I've said that, but just, either search it or let me know and I'll make a video for it. So. This is even worse than when I'm at home, my goodness. I may not be able to record this. Lovely spinning. If it hangs up while I try to make a part, I'm going to have to not record because this is really bad. Alright, so simple stuff. Start on the right line. We'll just sketch a circle. Does anybody care what size cut we have? What would you like? 1 inch? Okay. Alrighty. Boom, how long should we make it?
Since we don't have to do the calculation, 1.5 meters.
1.5 meters. Or 4 feet. We'll do 4 feet. Alrighty. So, in other simulations, all you have to do is just create your part and run it in. SolidWorks, when you're doing flow simulation, you have to cap the ends. So it only works with closed geometry. So if you have something open, it will not simulate it at all. Unless you're doing external flow, you can do external flow, and then it's all a bit different, but you can't do that with like this. So
Can you use ANSYS?
ANSYS, so the difference with that is you will create a volume that you work with. So here I'm creating a pipe and then like closing the ends, and then it's using the outside geometry to determine what's going on inside. In ANSYS, I'm just going to pull this in here. I'm going to basically pick the outside edges of the volume that I want to use, and then it just figures out what's inside there, discards everything else, and just gives me the volume. And then
I feel like it's a bit of a misnomer to say capping the ends. You're specifying the faces where you're going to prescribe fluid boundary conditions.
Okay.
Right. Yeah, it
You're
needs.
saying that you like putting a flow meter at each end. This is what's going on.
And you're telling the software where you're going to prescribe a condition. That condition might be the flow at that face, the pressure at that face, the volume flow, the mass flow, whatever. You're telling it where you're going to set properties.
Okay.
Right.
But that's not to say there is a flow going in.
Yeah.
Right. Yeah. So capping in the sense of making an enclosed space, but it doesn't behave in the real world as if I had a pipe with two caps on it. The caps are kind of just like nuggets, you know, they're there. So like he said, so you can kind of pick a place to put your boundary conditions.
Kind of like a function generator type deal.
Essentially, yeah. So anyway, there's two ways to do this. You can either open up your flow simulation, which will take a minute because I'm recording actually, maybe I'll. So right here, see the cap button, which is currently loading. So the thing that's nice about using the tool in SolidWorks is you can just kind of click where you want them to be, and it just done. It fixes it, it finds geometry. So it selects the planar faces, so that's when you rotate to the back. It wants the face of the end, so if you click inside or outside, or if you have some other geometry in here, you click like the back side of the flange, it's going to use that, but you might be cutting off a little bit of your pipe, so just make sure you're actually using the outermost edge. And there you can see it just kind of makes that cap straight through the center. The only thing it creates the cap here, and it's got some amount of thickness, which for some reason it won't let me change there. There we go. I want to make this like really thin. So when you go to select your inlet condition and your exit condition, you have to pick that inside face. So if it gives you a cap that's like an inch long and you're dealing with a shorter pipe, and that like starting point is important, you need to make sure that your cap is not taking out excess amounts of pipe. Otherwise, it will calculate everything correctly, but you might be off by a little bit because, you know, if you're looking for, you know, specifically within this 36-inch stretch, what's going on, and you're trying to compare that to something else, you're going to be off a little bit. Probably not by much, but just keep that in mind. So once you do that, you can specify here, just click OK, and it's good to go. So if you were going to go do it yourself, you'd have to do the first extrusion, which is your pipe, and then you'd have to go to the end, pick your geometry, then you'd have to convert your entities or whatever and like cap something through and make sure you actually close it. It's not hard, it's going to take you like, I don't know, a minute or two to do it. It's not a big deal, but when you use the lids feature, it just saves a lot of time, so that's why I say go there. You'll notice though, we have 3 solid bodies, so it doesn't merge it together. So it's not, when you would do an extrude, you wouldn't want to just extrude through the material that you have and tell it to merge. I think it will do it the same way, but I've run into some issues with it dealing with the lids, and I don't know what it's picky about. But like last year when we were running simulations for Uponor, it was something that happened where when we made the lid, it wasn't functioning right. But when we went in and just used the tool and had SolidWorks do it itself, it worked. The geometry was exactly the same. I don't know what the issue was. So if you're running into an issue with one method, try and switch it to the other, because there could be some little detail that's missing, or maybe you added something that's not supposed to be there. So sometimes you have to play around with it until you figure out what specifically is good or bad. Alright, so to run the simulation, you're just going to click Nope, and back to save the part. So do that. Let's go down here. Oh, and unfortunately, that plasma team keeps using that simulations computer, so I can't run their simulation. So you can talk to them about it specifically. Just kidding. Yeah, come on. It's like you're on that computer every single day, all day, running simulations for 36 hours.
It'd be like a machine shop at the end of the semester. You have to do a balance sheet. Or you got an hour and a half to run your simulation.
Good luck. I don't think I just did what I wanted to do, but whatever. Okay. So, new simulation. Um, the settings that you have to set up for fluids is more in depth. So if there's anything that's really different between the static simulations in the process and fluid simulations in the process is static simulations, you can kind of just do it and go. The fluid simulations, you need all your general settings in there. You have to do that beforehand because you're not just defining like what unit you want to use on your plots or where you want it to evaluate. It's kind of everything it has to use to evaluate. So we'll just name this one fluid. We'll just use default configuration. If you set multiple configurations on your part, which if you guys want to know how to do that, let me know. We can set those up so that when you run a simulation, like if you're going to run a simulation and you have to either just babysit it, you can set multiple different models to all kind of run one after the other, and it will, just run like a package of simulations. So if you know there's things that you have to, I have to do this, and then I have to do this, and then I have to do this, you can set it all up beforehand, just run it. But if you run into that, let me know. Otherwise, I don't know that I'll necessarily go over that. So, template, internal water. You can specify your own, but that's its own world. Alright, so you see a little bit different here. When you start running multiple simulations, you'll have to do kind of your setup for everything unless you're copying. So right here is where you're going to see a list of how many different simulations you've run or how many different setups you've put in there. So we're going to use this one here. So I guess we'll start with general settings. And this is where you pick either internal or external. We're doing internal, so we'll leave it there. Exclude cavities without flow conditions. For most of what we'll probably be doing, that won't be necessary to check or uncheck. But if you have a more complex part and there are cavities within your computational domain that don't have flow, you'll need to make sure that that's checked. Otherwise, it'll try to figure out what's going on, and it's not going to know what to do because there's no boundary condition there. But it's going to notice an open geometry and want to do something.
So if you would like to have a pressure transducer or something like that in a pipe, you need to declare that in the design work for it, you're going to have to big check the second box.
Yeah, more or less.
Because it's going to see that there's,
Yeah.
even if you have something physically there.
Mm-hmm. So yeah, if there's basically if you have like an empty space within the computational domain, which you can see right here as default is just a little box that I put around my part. We'll zoom in and check it in a few minutes, but that everything within that has some calculation running on it. So everything that you mesh is going to be within there. If I shorten that, it's only going to calculate up until the end of that domain. It's not going to calculate the rest of the part because it's there. It's only going to go to the end of the domain. But if I had some pipe that had some bend or something, and so I need to make that wider, but then I had some other empty cavity, that's where it would go. So it could be very well, as you're saying, like if you have transducers and stuff in there, and there's space in there, then we'll try to calculate that, but only if your domain's wide enough. Does that make sense? So like you might be able to eliminate that from your computational space, and you'd be fine. So right now we're not going to do any of this here time dependent, but if you're doing like a simulation over time, you'll need time dependent. Heat conduction, that'll come in later when we do heat transfer. Radiation, might not be using that at all. So that's good for analysis type. Reference axis, when I sketched, I used the front plane. So x-axis down here is what I'm looking at. So that's your direction of flow, either positive or negative x direction. So fluids, it has a pretty decent list of predefined fluids in here. If you need, you can click the new, and then this opens, and you can, I might do a video highlighting what the materials that we redefined for this, but if you need to do that, I would suggest videos because I don't do it often. So there's probably a lot more information out there. So, Syngas? No, unfortunately. But you could, if you have all the properties, yeah, you can go in there. So under gases, we have predefined. I mean, no, it's not. There's methane. There's methane. And stuff like that. So, regardless, liquids, predefined. This is where you got water. You have like some coolants. You know, so that's just your database of everything that's there. But you know, same with the static simulations. If you need specific material properties, you can go in. You have to do it a little bit different. It's not as easy as just going in here and clicking this button. There's another little step in here, but you can define real stuff. So we'll just do water. There's water. So confused. I don't have water. Liquids. Okay. That's a gas. Okay, so looks like we're going to use liquid nitrogen. All right. Oh my goodness, no, I'm done. Okay, water is already selected. It takes that out of your menu. So we're good. If you select something in here, it'll drop it down in this menu, and then you can't select again. Never mind. We're good. We can do water. So flow type, laminar, turbulent, or both. We're just going to do both because I'm not doing anything specific. But if you want to restrict it to specifically laminar, you can do that. Or only turbulent. Have fun. Cavitation, not going to be necessary for anything we do. That's if you're doing like something with a pump, you're trying to model a pump, or like you can model like turbochargers and stuff like that. If you're using a fluid, like if you have water or something with a pump and you want to be able to, you know, check for cavitation, you can do that. Otherwise, in any other method that we use, we're not going to be doing that. So,
if you choose laminar and turbulent, so do you have to predetermine where it goes from turbulent to laminar, or does it on its own?
I think it's just going to use the basic, like, you know, 2,000. Is it 2,000, 4,000 Reynolds number?
So what you would be doing is you would be opening up another set of equations that need to be solved to accurately predict turbulent flow.
Mm-hmm.
So, and so the reason why you wouldn't always check that is if you know everything in your system was so laminar that you're never gonna need to use those equations to solve the problem. And so from a computational perspective, you wouldn't check it, for those low runners and the problems just make it go quicker. But again, fundamentally what you're doing is when you check laminar and turbulent, you're adding, you're adding another package of equations to the ones that it solves. And then I would suspect, so you did do laminar and turbulent?
Yeah, because I'm not.
There are different choices of those packages to pick from. And so I would be surprised if there wasn't another option where it actually going to ask you to tell it what turbulence model you want to do. So,
Oh, I see what you're saying. I think that would be more in. I've not had to deal with it. I always just kind of assumed it used the default because I thought the
I'm
range.
curious what the default is. But
Yeah, I figured it was pretty standard, but
Isn't that similar to like where you have to use a bullet flat versus not using them?
all right. So basically, I think more or less the point is it just opens up the opportunity to simulate both if you don't know. And I can find out what specific point it decides that, yes, this is turbulent or no, it's not, and where the transition is and stuff like that.
But it's never asking or answering the question, is it turbulent?
No,
It's
it's
just always kind of solving these equations, or it's always solving these equations, whereby these equations are the equations with the added turbulent terms.
right. So
It just solves, it dumbly solves whatever package of equations you tell it to solve. That's the choice that you're making there.
right. I guess what I'm getting at is if you're close to the range, and if SolidWorks has it predefined as less, then you may need to check. Even though I'm saying like, okay, it's less than such and such Reynolds number, it's absolutely laminar. But if SolidWorks has that limit defined a little bit lower, then you might be skewing your result. That's what I was saying about like checking.
They're not going to have that limit specified. That's not
Okay. Fair. All right. So that's good for defining fluids. I guess when you're in here, if you select argon, you just click add to add it or remove to remove it. Same thing with water. If I remove this, then I can actually go select water. So, wall conditions. This is much more important when we're dealing with the heat transfer. So we'll probably overview this again. But you can select specific wall temperatures or rates or specific flux. So once we get into that, we'll deal with these. In roughness, you can specify, but again, unless you guys are doing a specific problem in which it wants you to calculate something dependent upon the roughness of the pipe wall, you can just leave that null. Initial conditions. So this is where this is basically what your starting point is. So when it has fluid coming in, this is what it's dealing with right here. So I just have room temperature and just room pressure. So if you know that you're dealing with like a hot steam pipe or something like that, you're obviously at a higher pressure, obviously at a higher temperature. Specify those conditions right away instead of trying to start with just the pipe. So if you specify that condition over the pipe, that's great, but your input condition is going to be less. So you're not going to be dealing with something that's already hot. If you're just looking at a section, you're going to be starting from room temperature and then running it through the system. So then there's all the heating and everything that may or may not be going on. So
Does room temp come up automatically? Room temperature come up?
this is just what's there. So I should say atmospheric. 101. Velocity, you can do that, or we'll specify that later. So, additionally, turbulence, if you have parameters, you can do that, but I usually just leave that as default anyway. Apply, click OK. So, the setup is, if you know what you're doing, pretty quick. Otherwise, if there's a lot of stuff that you have to change, that's probably the most time consuming besides actually running the simulation. Just making sure you've defined everything correctly. So for the rest of it, we have computational domain, which is the box that you see here. You can edit that, but there's no need to do this here. Fluid subdomains. If you have multiple fluids, that's where you're going to want to deal with a subdomain, but we're just doing one fluid for now. So boundary conditions. We're going to right click here, insert boundary condition. So faces to apply boundary condition. Right here, the type I have selected is the opening. And it has inlet mass, inlet velocity, inlet volume. We'll just do inlet velocity of, I don't know, 2 meters per second or something. And one of the problems you might be dealing with is whether or not flow is fully developed, or what that's looking like, or if you need to assume it's already been fully developed. So at the inlet, you're specifying here with this box whether or not you have fully developed flow, in which you'll get a little bit better idea when he runs through, if he doesn't not take fluids. So we can check that. It kind of takes away some of the additional stuff here that we'll have to be calculating. But that's because it's already been done. It's not assuming anything else. It's just saying we're good to go. So for this, what you'll need to do is select the inside face of that cap. So you're going to right click and use select other. So when you highlight over stuff, if you just right click, it deletes whatever you've highlighted so that you can see something else underneath it. So I've deleted that outside wall. Now I can see the inside of this cap. So I highlight the cap, and then that's when you left click to actually select that face. So otherwise you'd have to go in and do like a section view, but you have to do that before you open your boundary conditions, and it's just easier to use select others. It's the tool that's there to help you, so use it.
YouTube transparency too. Yeah.
Maybe. No. I'm still, if you look, I'm trying to get this one here. I've still got all of this is still orange. So it's still going to select that one. Transparency is going to be the same thing. So whether or not you can see it, the thing is that, like, if I made a glass tube, it's not any different than a solid tube, or not solid, but a solid wall tube. That, or I shouldn't say solid. They're all solid. If I make a glass tube or a completely that's the other word. It starts with an O. Opaque. The program's not saying like, oh, well, they can see the inside because it's glass. It's saying, oh, he's highlighting over this face. What face is this? It's not doing that for you. That's why you use select other, because you're saying, okay, I'm not looking at this anymore. I'm looking at this point. So, at any rate, select other. Don't want that. I don't want that face. That's one thing. If you do have it in this wireframe, it was just trying to select the inside wall, not because like when I hid the outside wall, it did the whole thing. But now that I'm in this view, I could also see the inside wall. That's not what I want there. So click this face. That's one condition. So you'll have to set another condition. For this one, I just want the the wall, and we're just going to do real wall. You can set your temperature, heat flux, roughness again. So if you're doing a part that has multiple different sections or multiple different pipes connected, or you have multiple flows flowing into one, and each section had its own parameters, as you specify them, you can change from the overall, what you set up in your initial conditions. You can go in and specify specific roughness or wall temperatures and such. So if you're only dealing with one and you already set it up before, don't worry about it. So you don't need to do it twice. There we go. Got that face there. And then we just need the backside here. So this is one thing that when you have the flow openings, you have the 3 inlet and you have the 3 outlet. You might think that you need an inlet and an outlet. When you do a fluid simulation, you need either an inlet or an outlet. And then whichever one you didn't specify, you have to just do as a pressure opening. So if we're taking this pipe, running a fluid through it, we specify the inlet condition from however we've defined that. Maybe we have some feed rate or something like that, and we're just draining out the other end. You're just going to use environmental pressure or environment pressure, because that you're just opening it up. At the end of that tube, it is static pressure. So you would have to specify that, oh, well, I'm putting, 3 cubic meters per second in, so I have to specify 3 cubic meters. I can work like that. So environmental pressure, that one. And again, select the other, right click on all the things you don't want to see, and then left click on the one you want. Again, in the general settings, we set up the basic. Yes. Yep. This is literally just saying that, okay, we've enclosed the pipe because it wants it, but this is really an open face. So, got those. So, these are all the inlet conditions. Boundary conditions, sorry. Every now and then, if you're not getting what you want, you might have to redefine these, unless you have something very specifically set and you know that is what it is. Sometimes it takes a little bit of playing around with. So when we're doing the simulation for Uponor, all the wall conditions, we didn't have data that said 100% what it is. So we had to take what we did know and kind of manipulate it until we got something that matched from the points that we knew, because we didn't know the wall temperatures specifically. So then you have to figure out and run the simulation. It takes some iteration to do that. So next thing, gushing. You want the wall mesh, by the way. There we go. The default in fluids has your mesh of 1 to 7. You can do your own definition of the mesh size. I've actually not had to do that. We just use the 1 through 7, and it kind of does everything on its own. To make it smaller. Was that just when checking for convergence? Okay. But we were using less than that to actually run the simulation, right?
More fine mesh, yeah. So if you go to advanced channel refinement for HFX, I'm not the other one, no. Where's it automatically end up?
Oh, I see what you mean.
You only need the 5% piece. The mesh.
So I would say most of the time, for for what you guys are going to have to do to present, you're going to be able to use this automatic. You will not need 7, I guarantee it. You will not need 6, I almost guarantee it. Most likely, depending on what you're doing, you're probably going to end up at 3 or 4, maybe end up at 5. But the way that it steps this down is pretty drastic. So you're talking about maybe 2 minutes to run at mesh 1, maybe 3 minutes to run mesh 2, and then it just kind of takes off from there. So your really low meshes are really quick, but in Fluid specifically, when you start upping that mesh, you're looking at a lot of hours to mesh and run. So pick something conservative to begin with. We're just going to do 1 because I know my computer's already running slow. And then you just run the result. So, new calculation.
Usually explain the new calculation after this too.
Oh, okay. Well, I mean, it's kind of.
The only reason I bring it up is Dave was mentioning it in the set simulations where we couldn't find the option, on this one, to see if it gives you explicitly the option to take the previous result.
Yeah, so it's kind of exactly as it sounds. You're either using what you've already calculated, it's kind of like a start point, and then continuing. What? Oh. Well, I broke it. All right. So even on the slow computer such as mine, even with the recorder running, you can see the calculation bar on the bottom is kind of running through. That's because I'm on that really low mesh. It would not be the same if we were running a higher mesh. My computer would probably just blow up. So start low. You'll want to do your checking for convergence right away, because one thing you don't want to do is sit and wait for fluid simulations to run if you don't need it. So you may as well check it right away, get some definition of what mesh size you need, and then only use that from that point on. Because it gets a little bit ridiculous, to be honest. So we have finished there. So your results, you have to go through and define everything in fluids for what you want to see. So in static simulations, it kind of has 3 basic. It has a stress, strain, and displacement. For fluids, you need to define all of them. So, come on. Yeah. I'm just trying to zoom out right now. It's thinking about it. Okay. There we go. Let's see. Cut plots is probably going to be the most frequently used. So you right click, new cut plot, and then you define the plane that you want to use. So you can use your first 3 planes that you have, and then if you need to offset that at all, you can do that. So you won't have to go in and create any reference geometry and use that. You can do it all right away from your cut plot tool. So we'll just look at the front plane, just kind of like straight down the center. And then contours here, that's what's going to be most descriptive, probably, of the variations you're going to want to see through there. So I'd suggest that. You can do isolines and vectors, straight lines. It's not, it doesn't demonstrate as much as you might want to know. And even though it's using the same information, it's a little bit harder to visualize. So you're better off just running with a contour. You can change the the number of color levels and the gradient and stuff. If you run into that issue, deal with it. Otherwise, the default's pretty good anyway. So we'll just look at, we might as well use pressure. check that. It'll calculate it here. I'll have to do a section. So here we go. So the pressure, we only have, 2,000 pascals difference here. So not much, pretty low flow, but you will have, as far as fluids go, you will have a linear relationship between your pressure at the beginning and your pressure at the end for a straight pipe.
I think you can change the lighting on that, by going on top.
Making it brighter.
Yeah, maybe do the seat colors.
There you go. Little tool right here. Apply lighting, not apply lighting. Make it brighter, less bright. That works really good for presentations, so that you can see all the gradients, because like we ran into vision the other day, sometimes what you see on your screen is not what you're seeing on the projector. So anyway, so that's cut plot. When you go into this cut plot, you can either add all the others, edit definition. I'm just going to edit the one I have. So it has most of these predefined parameters, which is what you're going to use most often. You're going to be looking at pressure, maybe temperature, maybe velocity. All the other fluid parameters are in here. So when we start getting into the heat, that's not it. I didn't actually specify heat. So when you do run a simulation with heat transfer included in it, it will give you more options here, which are all of the derived numbers from heat transfer. You guys you're in it right now. So all the other numbers, whether they've been calculated or derived or just empirical data, a lot of that actually comes through in here. You can select it. It always seems to be it doesn't have one that it wants, but I know there's some in there. Velocity, you can check all this. So I just say go through and kind of look through here and see all of the different parameters that you might want to know. If you want to look at viscosity, it's only dynamic viscosity. Reynolds numbers in there. You can do specific heat, which is it's going to be defined by your fluid anyway. So I think that would be more important if you're mixing, and you can check it as a specific point. But just keep that in mind. So if you know you need a certain value, chances are you can go in and pick one of these values. I want to know the turbulence length. Click OK. And then I can go in here and then click turbulence length. Check OK. And then there we go. Notice the length is extremely short here, but it will define that plot and plot it out for you. So the one thing I did run into is most of the time I'm looking for something specific. SolidWorks doesn't have that parameter predefined. So then you take the definition of that value, and then you can pick and check all of the others and then combine that to give you value. It's a little bit more work, but that's also possible. Like volumetric flow. Yeah.
So you had turbulence and then that's what you chose. Turbulent on there.
Yeah, but it would.
Would it still show that if you had just diameter only? Would it still show you the length of the turbulence?
Probably. It would probably just be 0. Because it's a parameter that's in there. Unless when you check that box, it's going to just eliminate that from your possible list of variables. Which I think, in fact, it might actually do, because I remember having a few more variables for heat transfer that are in there right now. So it might remove those from the list, but I'm not run 2 simulations just to check that, so I'm not sure. Let's see, you'd have to do your volumetric flow would be the same though. Yeah, so great. If I'm looking at just velocity or something like that, you'd then take the diameter of the pipe and figure out the volumetric flow. You might, no, if I cut it, it's not going to work. So trajectory is. I think there's a way to do it specifically where it calculates it though. Anyway, I just want to show this real quick. You can do trajectories in which you just select a face that they start from. You select the amount of trajectories. Click OK and it runs it. Let me hide this. Yeah. So if you're running with a straight pipe, you probably won't need it. I mean, you know where the flow is going. If you're doing some mixing though, that's where that becomes a little bit more intuitive or helpful. You know, you can see kind of like how all the things are mixing, what sort of interaction you're getting. So if you're trying to do, you know, I see most of the demonstrations I've seen, they have one pipe with one fluid, it's a little bit smaller, and then that's feeding into a larger pipe, and they want to make sure at the end that they have a very uniform mix. Well, then you want to go in here and see where your mixing is and see, you know, should I offset this pipe so that I get a little bit more spin there? You can play around with that. So that's where this is helpful. But if you're looking at pressures or temperatures or, you know, those types of variables, this is not going to be helpful. So there's a lot of other ways that you can pull information here. You can do point parameters. You can, you know, sketch a line through there and then pick that line to plot points across that line. I'll probably touch those in videos, but Fluids has a lot more capability to figure out what you want to know. So ask questions. I think, is it next Monday you do the description? So you'll do the problem description for the presentation after your static presentation, or your, yeah, static, that's not static, that's whatever. Mechanics and materials. Once you guys know what you need, let me know. I'll do specific videos for the information that you'll need to know. So, questions? Good.
We're doing a presentation.
I think you missed both. I'm giving the presentation for the presentation.
Yes.
I'm giving mine before you. Okay, so I'm on Monday, you're on Monday.
Right. Yes.